This is section 3A, part 2. We'll continue to do a few examples of related rates problems. In number 4, a man 6 feet tall walks at the rate of 5 feet per second toward a light that's 20 feet above the ground. When he's 10 feet from the base of the light pole, we'd like to find a couple of different things. The rate at which the tip of his shadow is moving, and the rate at which the length of his shadow is changing. I'm actually going to do part B first here. So when I set up my table, I'm actually doing part B. All right, so here we go. We've got this light pole that is 20 feet tall. Right, here's the light. And the man that's walking toward it is 6 feet tall. And then we want to know something about the length of his shadow. So if we imagine the rays of light coming down here, the shadow here is where the light gets blocked by the man. And let's see here. Let's call the length of that shadow x. I'd use s, but s isn't a good variable, right? All right. That's definitely changing. As is this distance. The distance between the man and the light pole is also changing, so maybe I'll call that y. I might need that as well. So what do we want here? What do we know, first of all? We know that the man walks at the rate of 5 feet per second toward the light. So my known derivative would be the change in y. He's walking toward the light, so the derivative of y with respect to time is, and I'm going to go with negative 5 feet per second, since as he walks toward the light, y gets shorter. Let's see, we're going for part B, so we'd like to know the rate at which the length of the shadow is changing. That's my unknown rate. And since I called the shadow x, that would be dx dt. All right, we'd like to know all of this when he is 10 feet from the base of the light pole. So let's see, when he's 10 feet from the base of the pole, that would be the y value, so that would be when y equals 10 feet. All right, so I need an equation that gives me a relationship between x and y. And in this case, I think I'm going to go back to similar triangles. If you're looking at this and thinking, oh, I'm seeing right triangles, so Pythagorean theorem, it is a right triangle, but notice that we don't know anything about the hypotenuse, and we're also not asked any questions about the hypotenuse. So if possible, I'd like to avoid including the hypotenuse in my process. If I just go with similar triangles, I can do that. So let's see, in a small triangle, I could say the ratio of 6 over x equals, in the big triangle, it would be 20 over this whole side, x plus y. So there's my equation. Just has x's and y's in it, which is exactly what I wanted. Before I take the derivative, though, I'm going to do some algebra because I would rather not do all these quotient rules. So I'm going to clear the fractions by just cross-multiplying. I'd get 6x plus 6y equals 20x. So 6y equals 14x. And I could even reduce that a little bit. Well, you know what? Let's just leave it like that. It's fine. All right, let's take the derivative. Everything with respect to time. So 6 times dy dt equals 14 times dx dt. Not a whole lot more I need to do with that. So let's plug in our information. Let's see, dy dt is negative 5. dx dt is my unknown, so that's okay. And you might be saying, but wait a minute, there's no place to put the 10. That's true. It looks like in this particular problem, dx dt isn't going to depend at all on where we are. It's going to be the same all the time. So negative 30 over 14 is dx dt, or about negative 2.14. And that would be in feet per second, meaning his shadow is getting shorter at the rate of 2.1 feet per second. Makes sense, he's getting closer to the light pole, right? The shadow is going to get shorter and shorter. All right, the second part, which is actually part A, says, find the rate at which the tip of the shadow is moving. So if you think about that point right there, the tip of the shadow, it's actually moving for two different reasons, right? It's moving because it's getting shorter, but it's also moving because it has to go with the man as he moves. So in fact, the location of the tip of the shadow is the total distance here, x plus y. So let's say t for the tip of the shadow would be x plus y. And so the derivative of t, the rate at which the tip of the shadow is moving, would be dx dt plus dy dt. The change in the shadow's length plus the rate of change as the man walks. And we know both of those things. We just calculated dx dt a moment ago. And dy dt back up in our chart was negative 5. So that would be negative 7.14 feet per second. And again, the negative just indicates that we're getting closer to the light pole in this case. All right, let's turn to example 5. An airplane takes off at an angle of 22 degrees, assuming a constant speed of 100 miles per hour during takeoff. Find the rate at which the plane is gaining altitude 30 seconds after takeoff. So let's see here. This is the runway. We have our plane taking off or going up at an angle of 22 degrees. And we have some questions about how fast the plane is gaining altitude. So let's call A the altitude or height of the plane at any particular time. And then let's see. This is the actual path of the plane right here, right? This is our airplane. So I probably want to label that distance that the plane has actually traveled. Let me just call that x. If I need it, I can label the horizontal distance as well, but I kind of don't think I'm going to need it. So our known rate is a little bit hidden this time, but it's there. It's the constant speed of 100 miles per hour. X is the position or the distance that the plane flew, right? So the speed would be the derivative of x. My known rate is going to be dx dt. And as the plane leaves, it's going to get bigger, so that would be a positive 100 miles per hour. All right, we were asked to find the rate at which the plane gains altitude. That's our unknown rate. So we'd like to find dA dt, the way I've labeled it in my picture. Again, always make sure you're using the same letters in your chart as the way you labeled your picture. And I want to do this when? 30 seconds after takeoff. So when t equals 30 seconds. Now, I do have to be a little bit careful here. I'll deal with it when I need to, but notice that I've got some units issues. This was miles per hour, and this is in seconds. So I'm going to go ahead and start with this, but when I start plugging information in, I'll keep that in mind. All right, I need a relationship between x and a. And once again, although I could write a Pythagorean theorem, the problem is that would get another variable involved, right? I would have to include the variable for this horizontal piece, and I really don't want that. So instead, I'm going to go with the trig function. The sine of 22 degrees would be a over x. Before I do the derivative, again, that's not the most algebraically easy way to do the derivative. I'd rather not have that quotient rule. I'm just going to multiply the x over. So I no longer have a quotient. All right, I'm ready to do the derivative. The derivative of x is dx dt. And remember that that sine of 22 degrees, that's just a constant, right? It's like it's a number. It's like, 5 or 6 or whatever. In fact, if we want to, we can even get a decimal value for it. If I put my calculator in degree mode, the sine of 22 degrees is about 0.3746. So that's a constant multiplier times the derivative of x. On the right-hand side, the derivative of a is dA dt. And it looks like I'm going to get a little bit lucky with this one because I can plug in my dx dt. It's 100 miles per hour, multiplied by that 0.3746. That's going to give me the dA dt that I'm trying to find. And I was really lucky. I never needed to use the 30 seconds, so the fact that the units were different didn't bother me anymore. So let's see here. That's going to be 37.46 miles per hour. So the plane is going up at the rate of, straight up at the rate of 37.46 miles per hour as it rises on that angle. All right, we have one more example. We'll take a look at example 6 here. All right, so here's our last example of a related rates problem. A model rocket is observed by a child standing 20 feet from the launch pad. At one time, the angle of inclination from the point of observation to the rocket was pi/6 radians, and it's increasing at the rate of 0.15 radians per second. Find the speed of the rocket at that time. So, you may kind of remember this basic setup from the last unit. We've got our observer, our child in this case, standing 20 feet away from the launch pad, and our rocket going up in the air. This distance doesn't change, but the height of the rocket does, so I'm going to call that h. And the observation angle, that will also change as the height increases, so we'll label that as theta. Keep in mind that although the setup looks very similar in terms of the picture, this is a very different problem from what you were asked in the last chapter. In the last chapter, we were asked to find the rate at which the angle was changing with respect to the height of the rocket. This time, we want to know how fast the angle is changing, or we're told, I guess, how fast the angle is changing with respect to time. So we have a whole new variable, time, involved that we did not have when we did this type of problem in the last chapter. All right, let's find everything that we need. At one time, the angle of inclination was pi/6. That's actually our when information, isn't it? That was a particular time that we're interested in. So when theta is pi/6, it's increasing, it being theta, at the rate of 0.15 radians per second. So there's the known rate. That'll be d theta dt. Again, notice that this is with respect to time now, not with respect to the height. And what I was supposed to find was the speed of the rocket. That's my unknown rate. The rocket's speed is the rate of change in its position, and the rocket's position is described by the variable h. So the unknown rate is going to be dh dt. How fast the rocket is moving is how fast the height is changing. All right, I need an equation relating my dependent variables, theta and h. And looking at this and everything that's been labeled here, it looks to me like tangent theta is h over 20 would probably be a good choice. I like the fact that the variable h is in the numerator. If you don't want a fraction at all, you can bring the 20 over here. It doesn't really matter. The point is that the variables are not in the denominator. But for those who are not crazy about fractions, if you want to rewrite that as 20 tangent theta equals h, you certainly can do that. All right, let's take our derivatives. Constant multiplier of 20 times the derivative of tangent theta, which is secant squared theta, and chain rule times d theta dt, equals dh dt. And it looks like this one's going to come real easy. We've got everything we need, right? We know the angle is pi sixths. We know d theta dt is 0.15. And if we put all that together, that will give us dh dt. Just a reminder, secant is the reciprocal of cosine, so whether you're using a unit circle or a calculator, I could rewrite that as 20 times 0.15 over the cosine squared of pi sixths. And make sure I'm in radian mode again here. If I take 20 times 0.15 divided by the cosine of pi sixths squared, I get 4. And let's see, distances in this problem, I think we're in feet, right? This was 20 feet. So since this is the rate of change of height, that would actually be 4 feet per second is the speed of the rocket at that moment. All right, that brings us to the end of Unit 3, Topic A.